This is the core question of the quiz. It's asking you to identify which statements correctly describe the strengths and weaknesses of different dimensionality reduction techniques, specifically t-SNE, isomap, locally linear embedding, LLE, and multidimensional scaling, MDS. This statement claims t-SNE is generally better than isomap for visualizing high-dimensional data because it's more efficient with large datasets. I found this to be false. While t-SNE is great for visualization, it's computationally expensive, unlike isomap, which can handle larger datasets more efficiently. This statement says locally linear embedding, LLE, works well for data that lies on a smoothly curving low-dimensional surface within a higher dimensional space. I found this to be true. LLE is indeed well suited for data with this specific characteristic, relying on locally linear relationships. Statement C suggests that multidimensional scaling, MDS, is a linear method, good at keeping the overall distances between data points correct. I found this statement to be false. MDS is actually a nonlinear method. Principal component analysis, PCA, is an example of a linear dimensionality reduction technique. Statement D says isomap is resistant to noise and outliers, which makes it good when the data is messy. I found this to be false. Isomap is sensitive to noise and outliers because it calculates distances along the curved surface of the data. I'm evaluating different techniques for reducing the dimensions of data, specifically focusing on those in sklearn's manifold module. I will examine their strengths and weaknesses to determine which is best for specific situations. This is crucial for visualizing high-dimensional datasets. I'm assessing the accuracy of several statements about the performance of dimensionality reduction algorithms. I'll analyze each statement carefully. This involves understanding the algorithm's behavior and limitations with various datasets. LLE shines when I have data points that form a smooth, lower dimensional shape within a higher dimensional space. Imagine a rolled-up piece of paper. It's two-dimensional, the paper itself, but exists in three-dimensional space. LLE excels at uncovering that underlying, simpler shape. This statement is incorrect. While TSNE, T-distributed stochastic neighbor embedding, is great for visualization, it's computationally expensive and struggles with massive datasets. Isomap, isometric mapping, often scales better for such scenarios. This statement is false. MDS, multidimensional scaling, is actually a nonlinear technique. It's designed to preserve the overall distances between data points, not just the local ones. Principal component analysis, PCA, is an example of a linear technique. This statement is also false. Isomap is quite sensitive to noise and outliers because it relies heavily on the distances between data points. Outliers drastically affect these distances, resulting in inaccuracies. I'll explain TSNE, T-distributed stochastic neighbor embedding. It's a powerful technique for visualizing high-dimensional data in 2D. However, I need to emphasize that t-SNE is computationally expensive and doesn't scale well to massive datasets. Think of it like this: it's great for creating detailed, insightful visualizations of smaller datasets, but it can become slow and cumbersome as the data size explodes. MDS stands for multidimensional scaling. It's a dimensionality reduction method. Now, a common misconception is that MDS is linear. It's not. It is a nonlinear technique that focuses on preserving the distances between data points in the lower dimensional space. I think of it as trying to maintain the original relationships between data points, even after simplifying the dataset. LLE, or locally linear embedding, is best for data that sits on a smoothly curved, low-dimensional surface hidden within a much higher dimensional space. Imagine a crumpled sheet of paper, low-dimensional surface, in a three-dimensional room. LLE excels at unwrapping that sheet to reveal its true, simpler form. Isomap is another dimensionality reduction technique. However, unlike LLE, it is sensitive to noise and outliers. It's important to remember isomap's dependence on geodesic distances, shortest path distances on the data manifold, and how noise and outliers can mess up these distance calculations, leading to a distorted visualization. This question tests your understanding of different dimensionality reduction methods like t-SNE, isomap, LLE and MDS. You need to determine which statements accurately reflect the strengths and weaknesses of each technique in the context of visualizing high-dimensional datasets. I'm looking for you to evaluate the capabilities of each method for handling large datasets, noisy data, and data with global versus local structure. This is the overall theme. We're exploring different ways to simplify complex, high-dimensional data so we can easily visualize and understand it. I see this as the title of a quiz focusing on different methods for reducing the dimensions of data. It sets the stage for what we'll cover. Let's dive in. This is the core question. We'll assess the truthfulness of statements about several techniques used to simplify complex datasets for visualization or analysis. It's a multiple-choice question which allows you to pick the correct answers from a set of options. This statement compares t-distributed stochastic neighbor embedding, t-SNE, and isomap. I'll be checking if t-SNE is indeed better for large datasets. I'll be using my knowledge of each algorithm's computational properties to assess this claim. Here, we're looking at locally linear embedding, LLE. I'll check if LLE works well with data that forms a smooth, lower dimensional shape within a higher dimensional space. Locally linear means it focuses on the relationships between nearby data points. This is about multidimensional scaling, MDS. I'll analyze whether MDS is a linear method and if it's effective at keeping the overall distances between data points accurate. Let's find out. The statement evaluates isomap's performance with noisy and outlier-ridden data. I'll check if it's resistant to such issues. I'll be reviewing the characteristics of isomap algorithm to determine the accuracy of the statement. This is the instruction indicating to select the accurate option from the provided statements A, B, C, and D. This simply shows where you would write down the selected choice after considering each statement. This question tests your understanding of four-dimensionality reduction techniques: t-distributed stochastic neighbor embedding, t-SNE, isomap, locally linear embedding, LLE, and multidimensional scaling, MDS. I'll evaluate each technique's strengths and weaknesses to determine which statements accurately reflect their properties. LLE is a great choice when you have data points that are locally linear. Imagine points arranged along a curved line. Locally they look straight, linear, but globally the structure is a curve. LLE excels at finding the underlying curve. This is because it identifies the local relationships between data points and tries to preserve these relationships when reducing dimensions. This statement is incorrect. While t-SNE is superb for visualization, it's computationally expensive and struggles with massive datasets. Isomap is often better in such situations. Incorrect again. MDS is actually a nonlinear technique. Linear techniques, like principal component analysis, PCA, are different. MDS focuses on keeping the overall distances between points similar after dimensionality reduction. Nope. Isomap is sensitive to noise and outliers because it relies on geodesic distances, the shortest distance along the manifold, like walking on a curved surface instead of a straight line through it. Noise and outliers can skew these distances. This question tests your knowledge of dimensionality reduction techniques, specifically t-SNE, isomap, LLE, and MDS. I'll need to recall their strengths and weaknesses to choose the correct answer. This statement is false. Isomap is actually quite sensitive to noise and outliers because it relies on finding the shortest paths, geodesic distances, between data points. Noise or outliers can significantly distort these paths, leading to inaccurate low-dimensional representations. Locally linear embedding, LLE, is a dimensionality reduction technique. I'll need to remember its properties to evaluate statement B. Isomap is another dimensionality reduction technique. I need to remember its characteristics for statement A and D. Multidimensional scaling, MDS, is a dimensionality reduction method. I'll need to consider its properties to evaluate statement C. This statement is false. T-distributed stochastic neighbor embedding, t-SNE, is great for visualization, but it's computationally expensive and struggles with large datasets. Isomap can handle larger datasets more efficiently. This statement is true. LLE works well when data points have a locally linear structure. That means that each data point and its neighbors lie on a low-dimensional linear subspace. This statement is false. MDS is a nonlinear technique. It's good at preserving global distances, unlike linear methods like principal component analysis, PCA. I'm analyzing different techniques for reducing the dimensionality of datasets. This is a core concept in machine learning and data visualization. This question tests your understanding of dimensionality reduction techniques, specifically t-SNE, isomap, locally linear embedding, LLE, and multidimensional scaling, MDS. I'll need you to evaluate each statement about these methods and decide which are accurate based on their properties. Let's see how well you know these algorithms. This statement is false. While t-SNE is great for visualization, it's computationally expensive and doesn't scale well to massive datasets. Isomap is often a better choice for larger datasets because it is more computationally efficient. This statement is true. LLE shines when you have data that forms a smooth, low-dimensional structure within a higher dimensional space. It excels at preserving local neighborhood relationships. This statement is false. MDS, or multidimensional scaling, is actually a nonlinear technique. Linear techniques, like principal component analysis, PCA, are different. MDS focuses on maintaining global distances between points in the lower dimensional representation. This statement is false. Isomap is sensitive to noise and outliers because it uses geodesic distances, which are easily distorted by noisy data points. This is the overall topic. I'll be evaluating several dimensionality reduction techniques to see how well they perform under different circumstances. This instructs you to choose all of the statements in the quiz which are correct.